Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find the area of the regular octagon? Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. Here's a regular octagon. Vertices A, B, C, D, E, E, F, segment G, H. All 8 sides are equal, and all 8 angles are equal. We want the area of this whole green figure using only its perimeter. The perimeter is 16, and a regular octagon has 8 identical sides, so each side is 16 divided by 8. That gives a side length of 2, and I mark side AB in blue to hold on to that number. Before cutting anything, let us find the octagon's angles. The interior angles of any 8-sided figure add up to 8 minus 2 times 180 degrees, which is 1080 degrees. The regular octagon has total interior angle sum 1080 degrees. Dividing equally among 8 vertices gives each interior angle as 135 degrees. Now enclose the octagon snugly inside a square. I extend the right and left sides and the 2 horizontal sides until they meet, marking 4 new corner points: top right, bottom left, and top left. Then I draw the 4 gold edges through them to close the square. Our first insight is this: subtract 4 congruent corners from the enclosing square. By the octagon symmetry, all 4 corner triangles are congruent. So if I measure one, I know them all. Let me focus on the top right triangle HI. Look at the corner point top right. 2 edges of the square meet there at a perfect right angle, so the angle of the corner triangle at that point is 90 degrees. At vertex A, the octagon's interior angle is 135 degrees, measured across to the straight right edge. The leftover between the octagon side and that vertical square edge is 180 minus 135, which is 45 degrees. A second insight now finishes the structure. Each corner is a 4-5-4-5-9-0 triangle. Slanted side of this corner triangle, running from H to A, is exactly one side of the octagon, so its hypotenuse has length 2. In a 45-45-90 triangle, the 2 legs are equal, and the hypotenuse is a leg times root 2. Turning that around, each leg equals the hypotenuse divided by root 2. Substitute the hypotenuse of 2 into that rule. Each leg is 2 divided by root 2. And next, I will clean up this fraction. Rationalize by multiplying top and bottom by root 2. 2 root 2 over 2 simplifies to root 2. So each corner leg has length root 2. Now, read down the right edge of the gold square. It is built from 3 pieces: a corner leg at the top, the full octagon side AB in the middle, and another corner leg at the bottom. Add those 3 pieces: root 2 plus root 2. The side of the enclosing square is 2 plus 2 root 2. The square's area is its side squared, so I need 2 plus 2 root 2, all squared. Let me expand this carefully. Factor a 2 out of the base first. 2 plus 2 root 2 is 2 times 1 plus root 2. Squaring pulls out a 4, leaving 4 times 1 plus root 2 squared. Expand 1 plus root 2 squared, 1 plus 2 root 2 plus root 2 squared, and root 2 squared is 2. That sums to 3 plus 2 root 2. Multiply by the 4. 4 times 3 plus 2 root 2 is 12 plus 8 root 2. That is the area of the whole gold square. Now turn to one corner triangle's area. 1/2 times leg, both legs are root 2, so it is 1/2 times root 2 squared. Root 2 squared is 2, and half of 2 is 1. So each corner triangle has area 1. There are 4 identical corners, each of area 1, so together they remove 4 square units from the square. Finally, subtract. The octagon is the square minus the 4 corners. 12 plus 8 root 2 minus 4 is 8 plus 8 root 2. That is the area of the green octagon. As an independent check, the standard regular octagon area is 2 times 1 plus root 2 times the side squared. With side squared equal to 4, that is 2 times 4 times 1 plus root 2, which is exactly 8 plus 8 root 2. Both methods agree. Numerically, 8 plus 8 root 2 is about 19.3. The enclosing square, roughly 4.8 on a side, has area near 23, and the octagon sits just inside it. That is exactly what we expect. So the answer is 8 plus 8 square root of 2. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.